So I'm Alan Talbot, and I was here last year and I gave a talk that spent some time on the subject of standard library containers. So I found that the containers are not as well understood as they should be, and I continue to see incorrect usage, even on the part of people who should know better. For instance, earlier versions of me. So programming, this thing about programming, right? It's kind of like being in a Robert Heinlein novel. You keep running into earlier, more foolish versions of yourself, right? So today I'm going to dive in a little deeper to that subject in hopes that you will teach me something. So we're going to look at 3 case studies, which I think are kind of interesting and actually fairly common scenarios, one of which is out of my work from just a few weeks ago. So this is for real. But first I'm going to start with a little history. This is a tale of letters. So a really long time ago, I was working for a company called New England Digital, writing music notation software. And we made a gadget called the Synclavier, which was the first professional digital synthesizer. I mean, this was back a ways. And the computer was a mini computer. The PC wasn't really a thing back then. I mean, you know, the Apple II was just out. The IBM PC was just out. DOS 1.0 had just been released. The computer was completely homemade, as was the OS and the XPL compiler. I assume you all know what XPL is. If you don't, it's a variant of PL1. So this computer had 64K of RAM. That's K. A lot of you don't know what K is, I imagine. But 8K was reserved for the OS, so I had 56K to work with. Needless to say, I had to be a little bit careful of my data structures. So then in the 90s, I was writing music notation software for myself, my own company, and I was writing it for the Mac. And I had a Mac SE, which, by the way, I still have. If anyone's interested in it, see me after. But it had 4 megabytes of RAM. That's M. But not only did I have to be careful of size, I also couldn't really depend on the OS to do a good job for me of memory allocation. It was really slow, so I would get these big chunks and do it myself inside the big chunks. Then in the 2000s, help me out here, is that what you call them, or is it the zeros? I don't know. What is it?
The noughties.
Oh, the noughties. I love this. Okay, excellent. The British spin, right? The noughties. I like that. And I had a 32-bit PC with 4 gigabytes of RAM. That's G as in B. But this was big data back then because I was working for one of the major digital map companies, making digital maps of the United States. And in order to get Texas into memory, I actually had to do this little trick. Some of you may remember there was some little like registry thing or something you could do to get the OS to give you 3 gigabytes instead of 2, because otherwise it says every process gets at most 2, even though there was 4 there. So I did that and I got it to fit. Turns out things really are bigger in Texas, even the digital map data. So once again, I was memory constrained, and speed was also very important. When I started working there, their product creation process took 3 weeks to run. That's W. I rewrote it, and after I rewrote it, it took 8 hours to run. That would be H. So performance matters. So as you see, I've had some experience managing memory and processor resources, but now I work for this railroad engineering firm, and I train railroad simulation software. And I just got a new computer a couple of months ago, and it's got 32 gigs of memory and lots of processors, right? And they run at over 3 gigahertz. So there's no problems anymore, right? Of course not. And yet, a few weeks ago, a customer was complaining that his simulation took way too long. So I ran it on my aforementioned super computer, whatever we call it now, and it took 7.25 hours, that's H again, to run. Now, mind you, my contributions to C++ have been all mostly pretty much about container optimizations and efficiency. And I've had the experience I just mentioned, and I gave a talk about this last year, so obviously I wasn't doing anything wrong with the containers, right? Of course not. So why even talk about containers? I mean, they're rather mundane, right? It's kind of like, I don't know, talking about sorting. I mean, is this worth a CppCon hour? Let's review containers real quickly. So you know all this stuff, right? I mean, we all know all this. I talked about it. Everybody's talked about it. You know, vector is like this, dec is like this, list is like this. This isn't news. I'm not even going to talk about the associative containers because we're sticking to sequences today. But the story's the same, right? And so these properties lead to these designs, right? These are the design choices that are baked into the standard library, right? For instance, vector has pushback and popback because they're order 1 mostly. And it doesn't have push front and pop front because they're order n. You know, insert, order n, et cetera, right? Dec has those things because they're order 1. And list is great. Everything's actually order 1, right? So this is all well known, so choosing a container is easy, right? Shouldn't be an issue. Everyone knows this. What's to talk about? Well, not quite. So these truths that we hold to be self-evident are entirely dependent on the particular situation. Used to be floating point operations were the things you had to watch out for. This is a long time ago, right? Limit your floating point multiplies. Today, it's floating points faster than integers, right? I discovered this to my shock, not all that long ago. But today, it's cache misses and heap allocation. Of the things we do lots of, those are the things that are really expensive that we need to watch out for. So it's not the case that big O complexity actually is the entire story. We have to look at the situation. And these are some examples of that. And like I say, I've covered this before. But what I want to do today is look at some very specific cases that are a little bit more interesting than just this. So I was driving back from an afternoon of rock climbing and a ridiculously good Mexican meal in Santa Fe with Howard Hinnant and Jonathan Wakely. And they were busy shooting down a proposal I had to add push and pop front to vector. And I won't go into that, but they convinced me it wasn't as good an idea as I thought it was. But in the process, they introduced me to a new container type. And I want to look at this a little bit. So let's start with this example. This is actually a pretty useful use case, and it comes up more than once in the software that I'm working on, and I suspect that other people have probably run into this as well. So we've got a lot of objects, and they all have a small queue that does something. So how do we implement this? Well, if that small queue doesn't have a maximum size that we can count on, we need something that will handle that, right? So the most obvious, well, before we talk about how to do it, let's look at my little test case. By the way, the standard library solution is the queue container adapter that requires pushback and pop front, which means it works only on list and dec, right? So I wrote this little tiny test case. And I sort of oversimplified the code. This isn't like the whole code, but I just wanted you to get the idea. Basically, we're going to have a lot of widgets, and we're going to thrash this in this outer loop reps times. And each thrash, we're going to go through and we're going to add some things to every queue, to every widget, and we're going to then take away some things. And those adds and subtracts are randomized. And they're randomized between one and some size that's an input to this algorithm. So this just sort of simulates some real world-ish kind of thing. But because we're randomizing between one and size, the size is going to kind of float around roughly. The size of the queue is going to float around size, at least order of magnitude wise. I guess. I don't know. Someone who's a theorist could maybe disagree. So I left out some of the code. I left out the random number stuff. But all right. So let's do this with list. It's the most obvious way. It's what the standard library sort of pushes you towards. It's this, Okay. Problem with list is, as we all know, right? We're going to allocate, and they're all over the place, right? In the heap. So your locality of reference in general is non-existent. So here's our widget. It's utterly simple to implement with list. I didn't use the queue adapter just because I wanted to keep it consistent across these examples. And it just does basically nothing much at all. How does it work? So I made a container of size 10,000 and I thrashed it 10,000 times and I set my rough queue size to 10 and I got these numbers on my computer. It doesn't matter. As long as you use the same computer, it doesn't matter what the numbers are. Okay. Now let's look at a vector. Because someone here is thinking, well, wait a minute, I saw your talk last year and you said don't use list for this, use vector. It's going to go faster for something small like this because, sure, you're going to be sliding stuff around in the vector, but it's small and it's going to be in cache and it's going to go fast. I don't get to use standard queue, but so what? Locality of reference will be excellent. I'll only get one allocation most of the time. Sometimes it'll reallocate if it grows, but then it won't move again if it doesn't have to grow beyond that, right? All that good stuff. So how does that do? Well, here's the code. It's still really simple, except that I don't have a pop front, so I have to do it, that way. And also, I did a reserve because we all know that vector works better if you pre-reserve something. So I pre-reserved size. Don't worry about how it got there. I cheated. I used a global. Nicely done, right? Time's down by 3.5. Memory's down by a factor of 5, right? I guess I'll get a bonus this year. But wait a minute, right? You say, there's some other container, I can never remember what it's called, right, that we could be using here. Oh, right, a deck. A deck has the best properties of a vector and a list, right? You can push and pop front. It's fast to iterate, right? So let's try it with a deck and see what happens. So, right? We don't know what's going on out there. The deck's complicated. I mean, at the very least, it's got a block. I mean, the deck has blocks, right? A linked chain of blocks. It's going to have at least one block, which we can't control the size of. And then it's going to have another allocation for its indexing thing, however that works, right? So some stuff's going to happen, but the people who write standard libraries are very bright, and they know what they're doing, and they think about this stuff, and they're going to make it work well. No question. So let's just try it.
Can I question on that? Which standard library are you using?
What's that?
Which standard library are you using?
For this particular test, I was using Visual Studio with 2017.
Yeah, I know. Good to know.
Yes. There are others, but this is the one I had handy. It's a drop-in replacement for list. We get back to this utterly simple code. Could have used Q, standard Q. How'd it do? Wow, that's pretty cool. I cut the time almost in half. But whoops. Memory just went up almost 3 times. In fact, it's more than half the original size using list. Now, sometimes this trade-off might be fine, right? And sometimes it might not. And something that you got to remember is the fact that your stuff's running fast and you're using all this memory, the fact that you're using all that memory may be causing somebody else's code to run slower, so the whole program may run slower. There's a lot of interactions going on out there. We're going to talk about that more later. But this is a possibility. So are we done? Are there any other options? Well, it turns out there is. So this container that those guys were talking to me about, it's got various names, but I forget, one of them came up with this name for it, but I like this name. It's called the Shifty Vector. So, how does this work? It's a vector. It's just like a vector, but the elements are in the middle of the space, of the capacity. And it can grow in either direction. It's got a push front, pop front, and when it hits the end, it shifts back into the middle if it needs to. It will need to because it hit the end. It will reallocate just like a vector if it needs to. Because it's got push front and pop front, it can be used with standard Q, if there were one. And we can see it work here, right? Pop, push, back, pop front, push back. I'll do that again. Right? So how does this do? Well, I don't have one. So I wrote this little sort of very kludgy simulacrum of one. I used vector and I made the assumption that I'm only going to ever push back, pop front, and because I didn't want to write this whole thing. I still reserve, and what I'm doing here is I'm keeping a front pointer. Otherwise it's just the same vector, but I'm keeping a front pointer. When I do a pop, I'm just going to return the front pointer and advance it. So now my empty test is the front equal to the end or not? Okay. Where it gets interesting is here. So push, so when I first wrote this, it was a little easier to read and it was longer, and I refactored it down into a nice tight code so it fit on the slide. It's very slightly harder to parse, but and I can go into this in detail later if someone wants to ask about it, but basically it's pretty simple. It always does a push back, and it always resets the front pointer. Turns out you have to do that even if nothing happens, because it turns out you cannot do a pushback. Let me rephrase it. If you do a pushback on an empty container, you will invalidate a pointer that you had previously set to begin. That is a little bit subtle, and it has to do with the way the standard's written. And it's probably not actually necessary that it work that way from a technical point of view, but it is how it works. So I need to preserve the front pointer, which I do with this X, which is just the offset from the beginning. And then if the size of this thing is at the capacity, I now have a choice. Either it's full and I need to just let it do its thing. It's a vector, it'll reallocate and move. Or I need to get rid of the ones I'm not using anymore that I popped from the front, which I do with an erase. Any questions about this? By the way, if you're paying close attention, you may notice that when I do a pop, I don't actually destruct the object. It's all right. They're just ints. This is just a test.
Yeah. Is this different from deck or DQ?
Yes. Yes, it is. This is very different from deck. And I'll if I have time or afterward, I'll go into that some more. The question was, is it different from deck? So that's how it works. How'd it do? So it's 2.5 times faster than deck, 4.5 times faster than vector. And we're back, of course, to using the same memory as vector because it is a vector. Nothing changes, right? It's just how I, messed around inside the vector that changed. So for this reason, I think we should have some more containers, and I think this would be a great one to add because I think this is a common enough pattern that it would be nice to have this in the standard library. So about now, I would have expected someone to put up his hand and say, yeah, but wait a minute. This is completely contrived. If I change any of these numbers, I'm going to get different results. Right? Exactly. That's exactly the point. Okay? Every situation is different. That's the one takeaway of this talk, is every situation is different. So you've got to measure. You can't depend on rules of thumb. They're not always right. Right? You can't depend on the STL design. It won't always lead you in the right direction. And you have to try different stuff. And you have to be very careful because your assumption that worked in the last 100 times you did it may completely not work for this situation. And sometimes it's rather tricky, and you got to really think about it. So just a little aside, there's a couple of other vector variants that I think are really interesting. One is fixed capacity. So that's different from an array. An array, a standard array, is fixed size. So you always have all of those elements there constructed. This is fixed capacity, so it's just like a vector, only it doesn't go out on the heap. You tell it how much storage you've got, and that's your capacity, and inside of that you can do anything you want. And when you hit the end, it does something about it, throws an exception or something. And then the other very useful variant would be local cache or short string optimization, or there's several other terms for it, where it does the fixed capacity thing until it runs out of room, and then it goes out on the heap just like any other vector. Both of these have been proposed for the standard library, and I would like to see them. I actually personally think that vector ought to give you these options out of the box, but sadly it doesn't. So the next example is a pattern which is typical of certain kinds of games. Now, I'm not a game person, so this isn't personal experience, but I also think that this pattern is probably much more widely applicable than just for games. So the idea here is that we've got a large, not even large, we've got some number of objects, and we have frequent turnover, right? Some things are getting blown away, some things are getting created, right? You think about spaceships are coming in, you're shooting them, but you're getting more ammunition. I don't know, I'm not a gamer, but the thing is that you've got pointers and iterators to this stuff all over the place. There's all these interconnections, so they can't be moving around on you, right? So deleting something or inserting something can't mess up your pointers. But order is typically not important. On the other hand, reliable iteration, fast iteration is important. Now, the only container that does this even remotely in the standard library is list. But we already know the list's limitations. We've talked about it. And the lack of locality of reference is going to cause not only poor iteration, but jerky iteration, which I have to assume is going to be bad for your video game. So I did a very simplistic example of this. I didn't show the code because it just does this. There's nothing tricky going on. I just wrote code that did this algorithm. The elements are trivial, but I wanted them to not have zero size. So they've got some size to them. I'm going to have count elements, and I'm going to thrash reps times, just like the other example. You can think of this loop, the reps loop, as the game cycles. And each cycle, I'm going to go through the entire list reads times, accessing each of the elements in turn. And then I'm going to delete every nth element, which has got to be some sort of worst case, right? And then I'm going to put back as many elements as I took out. And it doesn't matter where they go because order's not important, so they'll probably go in the end, whatever. All right? So I ran it with these numbers. Again, I had a container of size 10,000. I thrashed it 1,000 times. I did 100 reads, and then I took out every fifth element and put them back. And that took 14 and a half seconds and used that much memory using a list. And we know list isn't a great solution for this, but it's the one that's there. So, well, how could we do better? Well, it turns out there's a container called a colony, and this container is also being proposed for standardization. And the colony is designed to solve this exact problem, okay? These are some characteristics of the colony. What's most important here is that pointers and iterators are not invalidated. And memory for those, from elements that have been deleted is kept around and reused. But it also is smart because it uses blocks just like a deck. If a block gets totally empty, it returns it to the operating system. It has a separate data structure, which they call a skip field, which marks the deleted elements in such a way that to optimize iteration. So iteration is quite fast, even though it has to pay attention to the elements that aren't there. And then, of course, there's another structure that is there to identify the deleted elements so they can be reused. So this is this proposal and the implementation is written by Matthew Bentley. I'm not going to go into this in too much detail because, first of all, I don't know enough about it to do so. And second of all, he did a fantastic job of talking about this 3 years ago right here at this conference. I highly recommend you watch his excellent presentation about this. And this is a link to the code and the paper describing how to use it. So this is another one of these things, right? Who knows what it's doing? It's doing all this complicated stuff. But it's a container. It looks just like any other standard library container. It's a drop-in replacement. It was very easy to use. And I changed 2 lines of code in my little sample to change it from list to colony. And what happened? Well, 5 times speed up and marginally less memory footprint. And it's going to have significantly better iteration characteristics. So I find this quite compelling, and this is another thing I'd like to see get into the standard myself, because I think this has broad application. And there's lots of games out there. So where were we? Oh, right, okay. I was just saying that knowing all this stuff, I couldn't be doing anything wrong in my program with containers, certainly not. So I started banging away at my bug, my problem, and I noticed something. I noticed that when I ran the simulation at a 1 second time step, it ran fine. When I changed it to a 10th second time step, it ran 100 times slower. Well, that's not right because I'm doing 10 times as much work, storing 10 times as much data. It should have run 10 times slower. And it always had run 10 times slower, and suddenly it was 100 times slower. So this seemed like it could be a clue, but I'm not sure what it was a clue of. So I profiled it. Well, how about that? It was spending all kinds of time in vector allocation, but I'm doing all the right things. I'm reserving, I'm, move semantics, right? I'm, return value optimization, right? So why did it all, and it always worked. Why is it suddenly not working? Well, I noticed that it ran fine at 1 second with the electrical system on. And if I turned the electrical system off and ran it at 1/10 of a second, it ran fine. So what's the difference? Well, with the electrical system on, the program is generating a lot more data in memory, so it uses DEX actually to store all this logging information that it generates as the simulation runs. And I'm doing a lot more of that with the electrical system on because there's a lot more data to store. So I started to wonder if maybe because all this stuff was going on at once, what's happening is I'm using a bunch of vectors. Every time step, I'm creating a bunch of vectors and then they're going away. And then I'm creating a bunch of vectors and then they're going away. And I start to wonder if maybe the memory system, or between the cache and the memory system, it's thrashing and I'm reaching some saturation point. So I started to wonder if I was actually a victim of one of the things I spent a bunch of time talking about in my previous talk, which was loss of capacity history of these vectors. So let's revisit this and look at exactly what's happening in a vector. So when the vector's empty, there's nothing on the heap. You've got the vector body in your local scope. When I say local, I mean either in your object or on the stack. So there's nothing on the heap. When you add the first element, it allocates room on the heap for one element. We know this, right? But you can't always reserve the right amount. Sometimes if you reserve too much, you're going to waste memory. Sometimes reserving is not always an option. And so if you insert another element, you're going to get a second allocation, another element, you're going to get a third allocation. Now you've finally got room. It finally grew enough that you can put another one in without having an allocation, right? This isn't news, I'm assuming. Okay. With a reserve, right, much better. Just sits there until you have to add another one, and then it reallocates, and then it grows bigger than your reserve, right? But what happens when you're done with this vector and you need another one, right? Well, what do? We destroy it, right? We destruct it. We throw it in the trash, right? Who cares if it ends up on the beach down the coast? Throw it away. Poof, it's gone. And now we're going to allocate a new one with the original reserve. Notice it's not the same size, right? We had all this space, extra space, and now we don't anymore because we threw away that allocation. Right? So I started thinking, what could I do about recycling this thing? Is there some way that I could recycle this and not lose that? So not only not lose the capacity, which would prevent further thrashing as the vector grows, but also not lose the allocation at all, so I don't have to reallocate at all. Well, what if I move the vector into the recycling and clear it? So I've cleared it, there's no elements, and I've moved it over there. Neither of those things changes the allocation or changes the capacity. Right? Now when I need another one, I move it back, and there it is. It's empty. I stick my element in it. No allocation. No change in capacity. This is a very important point. The actual size, my actual capacity, has been preserved. So if I'm using a lot of these over and over again for the same kind of thing, the size of the vector will grow and it'll thrash around in memory until it reaches big enough. And then it'll just sit there. And if I have a bunch of them, well, they'll all tend to sort of float up to that size and then just sit there because they're big enough. And if every once in a while somebody overruns it, well, okay, they do. So how you actually would do this depends on your situation, but here's a kind of a simple little approach that I actually wrote and tried. And let you look at it in a minute. So the interesting things to look at here are that, if there's nothing in the recycling bin, then I'm just going to reserve, whatever size I would have reserved anyway. If there is something in the recycling bin, I'm just going to move it out of the recycling bin and then pop the back of the recycling bin. When I destruct, I'm going to clear it and push it into the recycling bin. Where it gets interesting is this guy over here, the copy constructor. So the copy constructor is assigning from another vector, but that assignment is not going to carry the capacity history. Right? If I construct a new vector with another vector, the new vector is going to be of the exact right size to hold the size of the vector I'm constructing from. And I don't want that. So I'm going to call the default constructor so that I get one off the recycling bin if one's available, and then just do an assignment. What's interesting here is you don't need to do this for the copy assignment operator. Why? Any thoughts?
It is already at size.
Right, it's already in play. That vector has already been used, so there's no reason to. It's already at size. So I implemented this exact code in the program I work on, the railroad simulator. And did it speed up? Of course it did. Over 12 times. So now it took 35 minutes, that's M, if you're keeping track, instead of 435 minutes. And this was not a simple example I whipped up for a lecture. This was the real world, real customer. And it made a big difference.
What about memory? I think you didn't free the memory, so consumed memory should be bigger than it was before.
So, right, the amount of memory that I was theoretically using, right? If you just measured the allocations, if you went and measured each allocation and added up that number, would be more with this scheme, because instead of using a vector that grew, by whatever the growth factor is. And, I don't know, I think maybe Visual Studio's is 1.5 or something. You've got something which is perhaps too big for your particular immediate use. But, oh, thank you, yes. I forgot to repeat the question. The question was, wouldn't we be using more memory this way? And the answer is, we're using more memory in terms of actual allocated pieces, but what was happening was I was creating all these holes in memory, because I create something, and then something else from elsewhere in the program would go here, right? And then I'd take it away, and the hole would be there. And then I'd create again over here, and then something would go there, on and on and on. So I was creating this big mess in the heap that was never getting compacted down. And I'm pretty sure that's why it inflated the way it did. Does that answer your question? So the takeaway from this for me was, as I said, don't make assumptions. You've got to measure. You've got to try several different approaches. And those approaches may be tricky, right? You may have to really think about it, to think of what's going on, because it did not occur to me for a while what could possibly be going on. And then I thought of this, and I tried it. And sure enough, wow, it worked. That was the problem. Know your containers, right? Basic complexity is not the whole story. And you need to know how all the standard containers work, and you also need to know what other containers might be out there in Boost or proposed for the standard library, or something that you can whip up on your own if you need to. And I think this is, if I were teaching a beginning computing class, this would be something I would stress, as one of the fundamentals of computer science. Know what's going on in the computer. Know what's going on in memory. Understand that heap allocations are expensive and that locality of reference is critical because of the way computers work today. And, it's going to be, if you know that stuff, you're going to be able to understand what's happening. And really, it seemed to me this was the theme of Andre's talk as well. You really have to think about how computers work these days. So that is how to choose the right container and why you should want some more. Yes?
How did you measure your memory usage?
Right. The question was how did I measure memory? I just used a standard. I used Windows call, operating system call, and asked for the peak commit. I can't remember the name of the call. Yeah, the peak commit of the program. So it's like the maximum amount that it.
The size of the footprint.
Yeah, the size of the footprint. Yeah, and I was running enough stuff that the size of the footprint was significant. I mean, it wasn't it wasn't a trivial amount. So it seemed like it gave me some reasonable order of magnitude.
Did you try to use allocators?
I did not. I know.
No.
Yeah. Thank you. I'm terrible at that. Dietmar's question was, did I try to use allocators? And I did not. The thing is, all of these, the whole world changes if you're using allocators, right? It makes it a different world with the same principles apply, but different answers and different solutions. And I was interested in situations where people didn't want to get into that and want to just use what's available easily. But I think that the same principle applies that, if it's not working, you need to look at all the tools, and a custom allocator is a tool that is specifically designed to address this sort of issue. Yes?
Of the non-standard containers you spoke of, like Colony, Shifty Vector, are there good quality implementations?
So the question was, are there good quality implementations of these containers that aren't standard in the standard? The colony implementation, I would guess, is probably very good quality. I don't know enough about it myself to know that for sure, but it's been looked at by the committee quite a bit already, and I know that he's been working on it for quite a while. Be a good question, you could ask. Look up the links, but I would guess so. The Shifty Vector, I don't know if any of those are out there. I'm thinking that I'd like to actually create one because I'd like to try and get it standardized. If so, it'll go through a process that will ensure that it's high quality, including going through Boost and such like. I see. I think you were next.
Yeah, I was wondering, other container types such as like basic string or maybe unordered multiset or something like that, how do those compare to the first two examples you gave? Do you have any idea?
So basic string isn't a container, and it's probably a good idea not to use it as one. I didn't explore it. The associative containers are kind of a different world because they serve a different purpose. I mean, you wouldn't want to use one for any of these particular problems. But when you're talking about something that is solved by a map, using an unordered map or other variants of hash map, of which there are some very good implementations out there, is certainly an interesting way to go. There was a very good talk about hash maps at C++ Now last year that I went to. You might want to look that up.
Thank you.
You mentioned that it's very difficult to make assumptions about which of the best containers for performance and memory, and that you have to measure it. Are there any tools available that allow you to put in different usage profiles, usage scenarios that will profile all the different containers automatically for you? Because that sounds like it would be very useful to time.
So the question was, are there tools that would allow you to investigate containers for your particular use? So I don't know the answer to that. I'm seeing a nod somewhere in here. I would think that in general, your particular use is different from every other particular use, and you're going to need to put instrumentation in some way so that you can tell what's happening in your particular case, because the situation that I was in, the scenario I explained here, was very particular, not just to my particular program, but to this particular use of it in this particular case. And it worked great 90% of the time, or 99% of the time, but just not this one time. So I don't know if there'd be tools out there that could help you with that. Because they wouldn't be testing the same thing that you're exercising.
That was the thing, you could actually think through your potential usage scenarios, put them in, and profile something that worked, you found the right in sort of your range of usage scenarios, and you could find the best container for that. So profiling.
I don't know, it sounds like a great tool. You should write one. Yes.
So with the Shifty Vector, it looked like when you added up elements, you still have to do some work to keep the elements in the middle. Is that something you could elaborate on?
Yes, so the way it would work, and I mean, something I forgot to mention about that is in my little implementation was very, very elementary and doesn't even do everything it needs to do. The real implementation would be much more efficient than what I was doing. But I believe that the way it would work most efficiently is that it wouldn't ever move until you hit the end. And once you hit the end, then the question is, where does it slide to? And I think the principle is you're going to slide it to the middle because you're going to assume that it's equally likely that someone wants to put something on one end or the other. It's possible that you could write one that where that was a user input to say, oh, I'm more likely to push things on the back, or I'm more likely to push things on the front, and then you could get some further advantage by knowing that. And did I repeat the question? I don't remember, but the question was, does it shift to the middle, and if so, is that the best solution?
What do you mean by time stepping of 0.1?
Yes, the question was, what did I mean by time steps, 0.1? So the program that this example came from is a railroad simulation, and it simulates trains running on tracks and the electrical condition of those trains, et cetera, et cetera. And any sort of a simulator, I mean, this is all happening in the real world continuously. So we have to somehow simulate that in the computer, but it can't be continuous. So there's a time step. You say we recalculate everything every 1 second of simulated time, right? So we say, okay, if the train is here and it's going, a foot a second, then 1 second later, it's going to be here. In between, there is no in between, because you're only simulating the train here and here.
When you up your points, you got this degradation.
Right. So if I'm simulating it 1 second at a time, and I get 100, it takes 100 seconds to do something. If I simulate it every 1/10 of a second, so it's moving 1/10 of a foot at a time, well, it should take 1,000 seconds, right? Because I'm doing exactly 10 times as much work. I mean, close enough. And in fact, it was taking 100 times longer because of the problem. But under normal circumstances, it would be 10 times the amount of work for 10 times the number of time steps. Other questions? Yes?
In the simulation, you said you added and took out the electrical input or whatever it was.
Yes.
Which constants became different. Did you go look at that code too?
So the question is, I found that if I took out the electrical aspect of the simulation, the problem went away. I didn't go look at that code because I knew what was taking the time because I profiled it, and I knew that the time was being spent allocating and deallocating vectors. The electrical data, in fact, all the data in the program is being dumped into memory as the simulation operates, and that's all being stored in DEX. So I knew it wasn't that directly. And it may be that if this wasn't the problem, I would have gotten to that eventually, but this turned out to be the problem, because once I did this, the non-linearity disappeared. So, a little aside here, why was I using DEX, not vectors or something else, to store all that data I was dumping into memory? Any thoughts?
Maybe growing big vector takes 2 times the...
Right. You can't use big vectors. When I say big, I mean big relative to your memory space. You just can't use them because of the way they grow.
Memory is max.
What's that?
Half of the memory is max.
Yeah. Well, except that it's not, because if your vector is half of memory and it tries to grow, it can't grow. It can't grow. Right. And if you have more than one of them, it just becomes impossible. DEX, on the other hand, use blocks which, relative to that sort of size, are very small. So it grows really nice and smoothly right up to the top of memory without any problem. And you can have a bunch of them, and they're all just allocating these blocks, and it all fills in. The problem is I was creating a bunch of holes in that, and it was just creating thrashing. That's my guess, anyway.
Then the ShiftyVector have the same problem. It's the size.
That's correct. The ShiftyVector is a vector. It's a variant of vector. Absolutely. Yep. It's not a different kind of container. But for the ShiftyVector example, so the question was, does the ShiftyVector have the same problem of growth? Yes. That was a different kind of problem, and that's a problem that I actually think there's a whole lot of. It comes up all the time where you want a small list of things, but you want a lot of them, and you want it to be high performance. But you can't count on saying, an example would be I've got an employee record, and I've got, we support up to 10 phone numbers, but I only want to, but almost everyone has 2 phone numbers or less, right? So I want to make room for 2 phone numbers, but but it has to be able to grow out there into 10. So that's where you want the local the short string optimization vector, for example. In this case, it's a queue, so you want the Shifty Vector optimization. Yes.
Thanks for explaining the difference between Shifty Vector and the vectors that you were recycling for this particular application. Approximately how big were they? Like, what is the median size?
So the question was, how big were these vectors that were causing this problem that the recycling solved? I can't remember if I actually measured that. I might have, I can't remember. But in general, they were on the order of hundreds of elements. They could be as small as tens of elements, but they were unlikely to be thousands of elements. So to give you.
Well, specifically on that, like byte size.
I guess the element, so the question was total byte size. I guess the elements were probably a couple of hundred bytes maybe, or less than 500 bytes, somewhere in there.
Okay, so significantly smaller than the page.
Yeah.
Okay.
Yeah. No, these things weren't small. I was generating quite a few of them, but they were ending up all over the place and chewing up memory. That's my assumption anyway. Other questions? You keep looking at me like you're gonna tell me something. Go ahead. I said I'm here to learn, so teach me.
Well, one thing I'm aware of is that this is why I asked when you mentioned DEC.
Yeah.
I asked for the standard library. The Visual Studio's implementation at least used to have a kind of the block sizes in the DEC. Right? The DEC is basically a vector pointing to blocks.
Yeah.
And the internal block size was the maximum of 256 or element size. And you would basically put the block size divided by element size elements in there. So if you have large elements in there, it's
Right.
basically a vector of pointers to elements.
Oh, okay.
And yeah.
So Dietmar's comment was that the Visual Studio library implementation of DEC, at least at some point, was using a very small block size. So it was 256. So you would either have, that would be depending on your size of your, or a single element, of course, if the single element was bigger than that. I personally wish that you could adjust the block size. I think you should be able to adjust the block size because I think that would allow you to tune it, and I think you'd see tremendous differences depending on how you tune it.
The reason it's not tunable in the standard library, by the way, is that the 98 standard did not correctly capture variable template arguments. If that had been fixed, and it was fixed in 2003, we could have just...
Dietmar points out that the C++ 98 didn't have variable template arguments properly handled, and that was the main reason why the DEC block size wasn't adjustable as a template argument, as I think it should be. So they couldn't fix that. Be nice to do another one that allows that. STD2.
Okay.
One more?
Don't you think that the containers that you suggested, like ShiftyVector or Colony, pretty special case containers, and usually your bucket peak in your project will be a vector, like something that's already in STL. And if you need those vectors, it's fine to import some library.
So So the question was, aren't these rather special case containers, and if you need them, you should go get them from somewhere, and meanwhile, the standard library has sufficient containers for most purposes. And you're right, vector, I mean, I said this last year, right? Vector's the one container to rule them all. Always start with vector. Not quite. I don't quite agree. It is true that these cover many, many cases, but I think these are compelling enough examples that it makes sense to have a few more. It is not easy to get this stuff right, to get these containers right. So if we can standardize it, we have a much better chance of having one that's right, generally speaking. Now that's not, I mean, this is a conversation we could have all night, and do have all night on the committee all the time, like what should and shouldn't be in the standard. And it's always a value judgment. But adding more containers, that, especially if they're variants of existing containers, like if there's a way, I personally think it would be great if we had one vector that did all this stuff, because really all you're saying is, I want a vector, but I want to control a couple of things. Like, does it do this, does it do that? Which would help to address that. Colony is a completely different container. And whether that has enough general purpose use or whether there's just enough games out there that to make it worth putting in the standard, that I can't answer myself, but it certainly has raised an interest, and it's still on the table. Now we're over a bit. I got us little signs. Actually, given our slightly late start, I was probably pretty close. Thank you for all your questions. Thank you for coming.